Hello. Today my team and I will be discussing a new and exciting advancement in the field of additive manufacturing. The team, 19035, has been dubbed the Laser Additive Manufacturing Engineers. Our sponsor, Honeywell, sent the QSync 200R laser powder bed fusion metal printer to the university, and our task was to create a heated build plate system, HBPS, that would integrate into the printer. Our mentor, Dr. Greg Ogden, has been instrumental in the project, and we would like to say thank you, Dr. Ogden. The bottom picture with the bright-eyed future engineers is us. I, Luis Arciniaga, Francisco Yareña, Peter Van Drielen, Edward Buster, and Marcus Scott. Our goal was to reach temperatures that no other generic build plate has reached before. We were aiming for temperatures as high as 500 degrees Celsius. The need for improvement on the creation of metal powder parts is due to the non-conformances seen in parts. These non-conformances cause early failure of parts and thus a need to reprint the parts. In future research, the HBPS will be used to print parts at different temperatures so they can be compared for quality of print. The quality of the print can be analyzed by observing the grain structure of the print, but to take it a step further, mechanical testing on the parts can be done to see if properties were changed due to the increased build plate temperature.
The control system was officially modeled as one giant thermostat, wired as an always heat until X temperature. This temperature can be set on the PID, and as a failsafe, a secondary device, a temperature limit controller, is set to shut off at a slightly higher temperature to ensure the safety of the QSync 200R machine. It is often difficult to make changes to the wiring or even open most electrical boxes due to the risk of pulling or damaging wires. We wanted to avoid this by making an open concept box within a box. This inside 3D printed box slides into the larger aluminum box completely so that no wires are pulled, stretched, or damaged. This also serves as an insulation barrier between the electronic components and the metallic box. Behold, these are the components that will go into our electrical box. They are just neatly laid out for you to observe. With none of us being electrical engineers, it proved to be a slight learning experience on how to wire things, especially with regards to AC, normally open and normally closed circuits. But it was that much more satisfying to see everything turn on and work in the end. We all grew up playing Legos, and it is extremely satisfying when components just simply fit nicely. This was essential to our design. Modularity and having components in the wiring be quick connect and quick disconnects, which this also in turn allows for easy upgrades and repairs.
The image here shows the broken out assembly of the mechanical portion of the project. Item 11 is the mounting plate that already exists within the QSync 200R. Item 8 is the lock post that prevents the items from shifting or rotating during operation. Directly on top of this is item 5, which is a sheet of insulation that prevents excess heating of the rest of the machine. Item 4 is the heated plate that contains the cylindrical heating elements depicted by number 6. Number 3 is a cover that prevents the powder used for manufacturing from seeping into the holes and crevices of the heat plate. Item 2 is the build plate, which is heated by conduction from the heat plate and provides the surface for which manufacturing takes place. Item 7 depicts the thermocouples, which protrude through the entire assembly until they make contact with the bottom of the build plate. And items 9, 10, and 11 are the various fasteners which hold components together. The heated build plate system was modeled using the finite element analysis software ANSYS. The CAD file of the heated build plate system was supplemented with a cap to simulate the metal powder bed and a chimney to simulate the build chamber. The convective boundary conditions were calculated using corrections of the Nusselt number, with the top of the assembly being subject to forced convection and the sides being subject to natural convection. The thermal conductivity of the powder was taken from literature. 2 transient simulations were performed with different loads, one with a heat flux from the heaters to simulate the heat transfer to the build environment and to add in the sizing of the heaters. Another with the temperature of the heaters to simulate the temperature of the plate and mimic operating conditions. A ceiling of 500 degrees Celsius was used to limit the impact of the heat on the MLab's operation, and as caking of the metal has been observed at higher temperatures. Unfortunately, we were hindered on our ability to complete the project. However, we were able to test some aspects of our system. With the exception of the temperature limit controller, we completed the assembly of the control system. For testing, we put the heating elements as well as the thermocouples into the heat plate as shown in the first image. We placed the build plate on top of the heat plate as shown in the second image and plugged the heaters and thermocouples into the control system. We then set the system to 60 degrees Celsius. The control system successfully operated the heaters and maintained the temperature at 60 degrees Celsius within 0.7 degrees. From this test, we successfully proved the functionality of the control system as a means to accurately set, control, and display temperature of the plate.
Turning this on would turn on the TLC, PID, and the SSR is on because it's saying that there's power and it should go through. So, let's put this up. Yeah, it's trying to heat it up. Green light, green light. Good. Now we ramp up the power to those.
We tested it in boiling water and ice water and it read pretty much dead on. And we tested the heaters in the plate and we set it to 60 and we're at 59.8 right now, so we're pretty much dead on there.
The major constraints of this project came from the need to limit the modification and hindrance to the machine. This drove the creation of a very unintrusive integration plan. The mounting plate, on which the mechanical assembly would be affixed, would have 2 holes drilled in it to allow for the passage of heater and thermocouple wires. These wires would pass into the bottom of the build chamber. From there, the wires would pass from the machine to the control box on the side through a gap in the bottom of the service access door. Then, the operator could set the operating temperature of the plate, allow it to reach this temperature, and proceed with the standard manufacturing process.
This project has tested our ability to work in a team and has made us better engineers. Our project could change the manufacturing process and become a major factor in materials development processing.
It seems that everything's connected. You guys ready? The green LED should turn on.